Hello everyone, and welcome to the ball rebound post-activity. So hopefully you completed the ball rebound pivot interactive with the nice rubber ball bouncing off of a wall. I think that's not something we would be able to do very easily in lab. You really need high-speed camera work in order to be able to figure out all of the times and what's going on, but it's still kind of an interesting thing to look at. And so what I wanted to do with you here was just kind of go through the nuances of how to do this and how to write it out, and of course all of the wonderful symbolic math models we can use for this, right? And to just kind of work through it, okay, a little bit. And also along the way to talk a little bit about pivot in case we do more of them this year so that you'll understand how it works. So in the problem, it said that there was a 283-gram ball that rebounds off the wall. And it wanted you to calculate, eventually, the average force the ball applies to the wall. Now, it is very important that you're looking for the average force the ball applies to the wall, right? Not the force the wall applies to the ball, which is related, but not identical, right? This is a tricky close reading thing that you got to do here. And certainly it's popped up on AP tests and things, and you got to make sure that you're doing the right one, right? Because that might change the direction, essentially, of your answer, as you'll see. So since this is a collision of a ball with a wall, it kind of makes sense that we might be using the one thing we know about collisions at this point, which is the impulse change in momentum theorem, right? Now, since they asked for the average force, we don't have to do any calc, right? Pivot's not really set up to do calc. They asked for the average force, which, if you remember, the average force is the constant force which applies the same amount of impulse as the real force does. Because in reality, if we were to somehow have a force time graph of the ball hitting the wall, it would be a spike, right, as the ball hit. It wouldn't be constant. But instead, we're going to look at the average force, right, in order to do this. Okay, that way we can use, again, the average force being the constant force which applies the same impulse. Right, so here we have impulse, average force times time, and here we have change in momentum. So be careful here, though. What change in momentum are we talking about? Well, we could be talking, there's two objects here. There's the ball and there's the wall. Well, must be the ball, for a couple of good reasons. First off, the wall probably doesn't move much, unless we knock it over or something. And secondly, we can only measure things about the ball in this pivot, right? So it better be the change in momentum of the ball, but you should be careful there. I mean, if you wanted to be technical, you could put a subscript on there, right? Change in momentum ball. Change in momentum is, of course, final minus initial. In this case, neither of them are zero. It's moving just before it hits the wall, and it's moving just after it hits the wall. So in both cases, it has momentum. Let's see here. Each momentum is a mass times a velocity. Since we're talking about the ball, this is technically the mass of the ball. Again, we could use a subscript here, right? M sub b, so that we know it's the ball and not the wall, but fairly obvious, I hope, at this point. Be careful, these are vector quantities, right? That's going to play into what we're doing here. If we then solve, that's the equation we need to be able to work with, right, to find the average force, except if this is the change in momentum of the ball, then this must be the force acting on the ball, right? Because the force acting on the ball would give an impulse to the ball, which would change the ball's momentum. So this is the average force acting on the ball, but that is not what the question asked for. The question asked for the average force the ball applies to the wall. You with me? Well, obviously those are related. It's one interaction, right? The ball hits the wall hits the ball. And so how are those forces related? Well, of course, we would then use Newton's third law, which says those forces are equal in size and opposite in direction. So do you see how I switch this? right? So this is the average force the ball applies to the wall, right? And I just made it the negative of the force that the wall applies to the ball. It's hard to say that, right? So that's why the extra negative's thrown in there for Newton's third law. You could do it here, or you could, work this out and then slap on the negative afterwards, right? Or the direction, pick out of the video, okay? But in terms of the math. So that means we need to know several things, right? We're given the mass, 283 grams, which, by the way, needs to be, of course, converted to 0.283 kilograms, because you're not going to get newtons of force out if you're not in kilograms, meters, and seconds. Right? A little hint I tried to put into the pivot, because everything in the pivot was actually in centimeters and grams, so you got to convert everything to meters and kilograms, respectively. So we know the mass, so we've got to measure three things, the velocity of the ball when it hits the wall, the velocity of the ball as it leaves the wall, and the time it's in contact with the wall. Now, the time it's in contact with the wall, I hope, was fairly easy to do with the stopwatch, right? And the high-speed video, and you can go frame by frame, right? And figure out exactly how long it's in contact with the wall. Hopefully, you put the ball at the frame where it first touches the wall, you zeroed the stopwatch, and then you forwarded to the point where it just leaves the wall. And the time should be right on the stopwatch, right? It's one of the nice things in Pivot where you can do that zero thing anywhere you want it to, right? Reset stopwatch. So then the question becomes, okay, if that's how we measure delta t, how are we going to measure the velocities? Well, Pivot does not allow direct measurements of velocities. There's no motion detector or encoder wheel like on our new fancy carts or anything like that. So you basically have to be a little crafty here. First off, you've got to assume that the velocity of the ball is constant when it's not touching the wall. Okay? So before it hits the wall and after it hits the wall. Now, technically, it's moving in a parabola, so only the horizontal velocity is constant if we can neglect air resistance. So we're going to do some things to help us out there to make sure that our data is as good as possible, right? To try to keep it in the as close as possible constant velocity realm. But if we can assume it's a constant velocity, then we can just calculate the speeds in and out, and I do mean speed here, just by going distance over time. Okay? Distance is how far the ball moves. You've got a ruler for that. Time, again, using the stopwatch. Right? So we can do it once for when it's going into the wall and once for when it's coming off of the wall. Right? So here's some ideas that you might want to think about for this one and for future pivots. Okay? Expand to full screen. I showed you that little button in the corner. It does help to see it, especially if you're trying to do this on a phone, right? But even on a smaller laptop or iPad or something like that, right? It's going to help you to see things if you make them big. What distance should you use here? Well, you really could use any distance. You could use the ball the entire time it's in the screen until it gets to the wall. But why? Right? Why not choose a nice distance, like, say, 10 centimeters? And then if you're only going to use 10 centimeters of its motion from the moment the ball comes into the screen to the moment it hits the wall, why not use 10 centimeters near the wall? Right? That way, any frictional effects happen earlier. And the same thing when we're finding the final velocity. Why not use 10 centimeters just after it leaves the wall, rather than 10 centimeters, way to the left? Does that make sense? Of course, you can use the stopwatch reset button. So you set you use your ruler, you get the ball so that it's right at 0. Make sure you're using the 0 line, not the edge of the ruler itself, okay? The edge of the image, okay? But the actual 0 line on the ruler. Sometimes that can be an issue. And put it right on the edge of the ball. I'd use like the right edge of the ball probably. 0 your stopwatch, reset it, and then fast forward it till it goes exactly 10 centimeters, or as close as you can possibly get. Right? If it's not very close, then you might want to use some different frames, right? Move it a little bit, try it again, see if you can get one that's pretty darn close. Then your time is just whatever it is on the stopwatch, sorry, and your distance is 10 centimeters or 0.10 meters, right? Remember, you got to be in meters per second to eventually get to newtons. Here's the key thing, okay? Key mistake that you might make. Momentum is a vector. It's a vector because velocity is a vector. And while we might be calculating speeds of the ball here inside a pivot, in the equation, they've got to be velocities. Granted, it's one-dimensional motion, but there's still two choices of direction. It could be going right and it could be going left. Conventionally, we call that positive and negative. Well, going into the wall, it is moving to the right. So the initial velocity should be positive. But after it leaves the wall, it is moving to the left. So the final velocity must be negative. Did you do that? Right? So the final velocity has to be negative. Notice what that does. That means you get a negative minus this, right, which is a positive. So they end up actually adding together, if you will, and becoming a bigger negative. Right? If you don't do that, if you just put in numbers, you're going to end up subtracting instead of adding. And that gives you a whole different answer. It was one of the choices I gave you inside of the pivot to see if you fell into that trap, right? Oftentimes, this manifests itself in these kinds of bouncing things. They often, on a test, will say, let's make this a perfectly elastic collision where kinetic energy is also conserved. In other words, so that the ball comes off the wall with the same speed it goes into the wall, right? In that case, if you don't deal with vectors, if the velocity off the wall, if the speed off the wall is the same as the speed into the wall, your change in momentum will be 0. At least it appears to be 0, right? And you'll say, oh, the average force was 0, which makes no sense. And there's your answer, right? But it won't be that way if you deal with vectors. Going one direction, it's positive. Going the other direction, it's negative. Or vice versa, depending on which way the diagram's drawn, right? So you got to get the vector nature of this down, right? Very important. Okay, and like I've been saying all along, to get an answer in newtons, you need kilograms, seconds, and meters per second. All right? Otherwise, you don't have newtons at the end. So be careful with the units in your pivot. Hey, all of these things, right, are kind of little things to help you make the pivot work well. And some of these are going to pop up again in other pivots we're going to do, right? Really, the two main things we use in here are rulers and stopwatches, and sometimes variations of protractors to get angles, okay? Those are the three main devices that we use inside a pivot to measure things. Everything else we kind of have to calculate with pivots, okay? Because they don't have a really nice way of measuring velocities or accelerations or things that we use high-tech, motion detectors and encoder wheels with. So I went through all of this so that, for two reasons. A, if you did not get an answer that was close to my theoretical answer inside of the pivot, you might want to go back and redo some measurements, right? And see if you can't get a better answer. Use it as a practice, if nothing else, right? You can always go back in, recheck things. But even if you did get good results, just as a reminder so that in future pivots, right, maybe you'll use some of these techniques and be a little more careful with what you're doing. So I hope this all made sense and you did well on the little ball rebound activity.